So I would like to welcome everybody to this meeting. Actually, it's very happy to see actually a lot of you has been partying through the Boston and the Harvard, MIT, and all these brands, all these schools. I want to welcome everybody to this meeting on representation theory, Calabi-Yau manifolds, and mirror symmetry. So this is a hybrid format, and I find this it's a wonderful format because everybody can sit here and listen to some of the talk and presentation here and also online. Our first speaker is Professor Shing-Tung Yau, and the founder of this institute, and his title is the Strominger system through conifold transition. So let's welcome Professor Yau. Thank you.
Well, thank you. Now, in this talk, I want to discuss Calabi-Yau manifold in geometry and physics, and discuss the geometry of Calabi-Yau manifold outside the Kähler regime. Of course, this is somewhat related to mirror symmetry. I hope it's not completely finished. But in any case, I think it is an interesting area that I think one should explore. So here, a Calabi-Yau manifold simply means a complex manifold with trivial canonical line bundle. So for most of the case, we just simply say first trend class equals 0. But of course, we have to be careful what first trend class equals 0 mean in a non-Kähler manifold. In general, we would like to make it to be like in the DD bar cohomology is equal to 0. That means the trend form is equal to DD bar of some function. A very important class of Kähler manifold, or Calabi-Yau manifold, of course, Kähler manifold. They emit Hermitian metric. Where omega is Kähler, and these are called Kähler manifold, of course, and the Kähler class. And as you may know, of course, in 1976, I showed that there exists a unique Kähler metric in each Kähler class, so that the Kähler class of G pi is the same as a given one, and so that Ricci curve is equal to 0 of this Kähler class. So this was obtained by solving the complex Monge-Ampere equation. Omega pi to the power n equal to exponential f times omega n. So this is a complex Monge-Ampere equation. Of course, now we look at it, it's rather straightforward and reasonable, easy to do. But in those days, we struggled for a long time because the whole subject was not developed. This metric now called Calabi-Yau matrix. And the important point, of course, is that the holonomic group of this manifold is sitting in SUN because it preserves the holomorphic N form. So most Calabi-Yau manifold, if it's simply connected, it has a holomorphic N form. And this holomorphic N form reduces the holonomic group from UN to SUN because it is invariant under parallel transportation. Well, in the early 1980s, it was realized by some of my physics friends, Kähler, Horowitz, Sch-Minger, and Ritten, that these are fundamental objects in string theory, and presumably you can understand a great deal about the universe. Well, this is very important connection whether string theory is right or wrong. It has been a very fruitful enterprise for the last 50 years. So in this talk, I will discuss, among other things, some idea from physics that I hope will be helpful in understanding non-Kähler Calabi-Yau manifolds. Well, first of all, we would like to know what kind of objects are important, are canonical. So maybe you can call it uniformization. You said the analog of Ricci-Fleck Kähler metric on non-Kähler, well, analog of that on non-Kähler Calabi-Yau manifolds. So an important generalization of Kähler metric turns out to be Gottesson metric, which was introduced by Gottesson. Namely, you take a 1-1 form alpha, which is positive definite, but it's not Kähler, it's not close. But it satisfies the equation alpha to the power n-1 is dd bar close. Well, this one turns out to be very easily exists. Namely, given any such one-one form, you can always conformal deform it to satisfy this equation. So every complex manifold admits such a metric. And this makes life easy because it always exists, but as a result, it's not as strong because we don't know how to play with it in general. There's, of course, some interesting things that we can make use of this condition, but not that much. But then there's a stronger notion called balance metric, introduced by Mary Louise Michelson about 45 years ago, I think. This metric is called balance if the associated one-one form satisfies the stronger condition. Alpha to the power n-1 is closed. So this is a topological condition that, closed forms. And this is much stronger than the dd bar alpha to the power n-1 equals 0 condition. So in particular, it may not exist. So this makes an interesting class of manifolds between Kähler manifolds and non-Kähler manifolds. It's a reasonable large class of manifolds, and yet it's not the whole thing. So that makes things interesting. And Mary Louise actually gave a rather interesting characterization under what condition that a balance metric exists. And several people follow, and Alexander and his co-author show that the existence of balance metric is invariant under birational transformation. So this makes it very interesting and tempting. In other words, they prove that if you take a balance manifold, you take a blow up or blow down, the existence of balance metric on one of them implies existence of balance metric in the other. So this is an interesting phenomenon. It's very nice compared with Kähler geometry, because we know that in Kähler geometry, it's not true. Existence of Kähler metric is not invariant under birational transformation, but the balance metric does is invariant. So this, I think, this should mean that balance manifolds should play a rather important role in birational geometry, but it has so far not been explored yet, which I hope will be understood in the future. Anyway, so it's natural to ask if a version of the Calabi conjecture holds for this class of manifolds, either Gottesson manifold or balance manifolds. Gottesson conjecture there should be a Chern-Ritchie-Fleck Gottesson metric, which amounts to proving this similar more complex Monod-Ampere equation without Kähler condition. And this was solved by 3 authors many years ago, about maybe 15 years ago, which is a nice argument. And they show that every compact Calabi-Yau manifold emits a Gottesson metric whose Chern-Ritchie curve is equal to 0. This is very nice, except that this metric is not canonical compared with the one on Kähler geometry, because the Kählerian helps you to make the metric to be rather rigid, cannot move around. But given a Gottesson metric, you can move around quite easily. It's not expected to see that this metric is unique, even modulo automorphisms. So one needs to find some way to make it more rigid in order for it to be applicable to questions in algebraic geometry. So I think there's still some progress to be made in this direction. So a natural way is try to pin down the metric is probably impose some further conditions, like minimizing some energy or like Yang-Mills energy or whatever, but it has not been done. Well, we come up with some other approach. Instead, we look for string theory for motivations, and string theory has been a very inspiring subject to complex manifold and to Kähler manifolds. Well, it turns out non-Kähler Calabi-Yau manifold does play a role in string theory, since they can be used to construct string theories with fluxes. So the original Calabi-Yau manifold has no flux, which we shall see what that means immediately. There's a free form in the case of string theory, and in the case of complex manifold that we're talking with, we are taking this H. H is a free form defined by I d minus d bar operated on omega. Well, this guy is trivial in the case of Kähler geometry because omega is closed. And therefore, there's no flux in the Calabi-Yau setting when the manifold is Kähler. But it is non-trivial in non-Kähler manifold. So H could be non-zero. This means that it could be a theory with flux. The free form is non-trivial. The equation of motion for supersymmetric compactification of heterotic string were obtained by Andy Strominger, my friend, in Harvard now, and we can show a little bit about what he said before. In the original proposal for compactification of superstring, compactification here means that from a 10-dimensional manifold, we reduce the theory effectively to 4 dimensions. And so we have to make the 6th dimension to be compact, to make it small. And this was done by Kähler, Horowitz, Hull-Strominger, and Witten. They look at the metric product of a maximal symmetric 4-dimensional spacetime, which could be Minkowski spacetime. And they take product with a 6-dimensional Calabi-Yau vacuum. And this together form a 10-dimensional spacetime. They identify the Yang-Mills connection with the SU3 connection of the Calabi-Yau metric and set the dilaton to be a constant. And the whole thing becomes the standard Calabi-Yau geometry. And at this, around the same time, when these 4 authors did their compactification, Ken Rurenberg and I proved the following theorem, that a slope-stable holomorphic vector bundle on a Kähler manifold emits a unique Hamilton-Yang-Mills connection. This was also proved by Simon Donaldson in his thesis in 1985 for algebraic surfaces. And after our theorem proved, he also generalized it to general projective manifolds using a restriction argument. And well, actually, I proposed to Ed Witten about using this one for string theory for the heterotic string theory. At the beginning, he didn't think so, but then he and later with his students, they proposed to use high-rank bundles for strongly coupled heterotic string theory so that the gauge group can be SU4 or SU5. And these are meaningful for them because they want to study the grand unified field theory with SU4, SU5 gauge group. At around the same time, Andy Strominger studied the heterotic superstring background with spacetime supersymmetry and non-zero torsion by allowing a scalar walk product situation. So in the original setting by the 4 authors, they just take a trivial product. Here we take a walk product. So as you see it in here, it is a 10-dimensional spacetime. There is a walk product of a maximal symmetric 4-dimensional spacetime, for example, Minkowski spacetime, with an internal space X. And the metric on the product has this form that I wrote down here. Notice the scaling factor exponential 2 dy. The y depends only on X and on the compact manifold internal space. And the fiber is still the Minkowski spacetime, except by multiplied by scaling factor. So, but it's multiplied by scaling factor, so it's a walk product. And it's not quite the same as a product, as a trivial product, metric product. So this gives rise to a torsion on Gij. Previously, there's no torsion, which gives rise to a Kähler geometry. Here, because of the existence of non-trivial dy, this gives rise to a torsion geometry. And because we are dealing with heterotic string, so there's a bundle also over X, over the internal space, which equipped with a Hermitian-Yang-Mills connection. The Hermitian-Yang-Mills connection is described by this equation 1. So the curvature of this bundle, wedge with omega square is equal to 0, and it's holomorphic vector bundle. So the 2CO part and CO2 part of the bundle of the curvature is equal to 0. So this gives rise to a bundle and the metric Gij and the bundle. So this is good. In this system, there are several quantities that appear. One is a H that I described to you, the free form. This is called the torsion in the free form in heterotic string theory. And capital omega is a holomorphic free form that we assume to exist. And the norm is taken with respect to the metric. So we have this metric Gij that I described to you written in this form. Okay, so in order for the ansatz to provide a supersymmetric configuration, we introduce a spin law epsilon so that it satisfies the three equations. This means supersymmetric because the supersymmetry acting on psi and lambda and chi are equal to 0. One is a gravitino, one is a delitino, one is a Grunner. And so we have an interesting setting which make the whole subject to be supersymmetric. It turns out there is a equation that must satisfy, namely dH should be equal to the trace F wedge F minus trace R wedge R. This is called the anomalous equation. And this equation is actually rather complicated mathematically speaking, but it is the equation that link the metric Gij with the metric on the bundle. So you see omega is the metric on the base. H is defined by d bar minus d acting on omega. So H is coming from geometry, from Gij bar. And F, of course, is the bundle curvature. The R is the curvature tensor coming from the metric. So this equation links the metric on the base with the bundle metric. This is a way that they link that together. So we can rewrite that equation to be I dd bar omega to be this equation 2. The previous equation with H can be written this way. The supersymmetry turns out to require this d star omega to equal to this equation. This was written down by Strominger and just like that. Turns out it was observed by Junli and myself. It's much better to rewrite this equation, the supersymmetry equation, to be equation 3. This becomes much more transparent for the free manifolds, namely the norm of omega conformal to omega squared should be a closed form. So this is good. This now links balance metric with supersymmetry conditions. So omega squared is supposed to be positive definitely, and the balance condition exactly says that this metric is closed. So now we are getting into balance condition, and so we call this system to be Strominger system. The first equation is a condition for supersymmetry, and in terms of mathematics, it's called a balance metric condition. The second equation is a Yang-Mills condition. So the first two says that it comes from holomorphic bundle. The other equation says that it says a Yang-Mills equation. The last equation is called anomaly equation. It's coming from supersymmetry consideration. And this defines an interesting, beautiful system of equation linking the bundle with the metric. The first two are defined by itself. The first one is defined by the metric. The second one is defined on the bundle, but the last one links these two together. So now we have a string theory with flux. Namely, we have non-trivial dilaton, which was equal to constant before when we are dealing with Calabi-Yau manifold. Here is non-trivial because it's not Kähler. So this is a very interesting system equation that attracts me since 1986. So my friend Andy Strominger showed me this system, which encouraged me to look into it. But unfortunately, he was not able to find a non-trivial, non-singular solution of this, and I did not know how to do it for quite a long time. And in fact, I asked most of my postdoc who worked with me since that time, was not able to solve it for a long time. So, well, this is an interesting equation, which is I consider as an analog to the complex Monod equation, appear in the Calabi conjecture, and also it appear with this Hamilton-Young connection. So I'm tempted to understand this system by itself. So as a system in geometry, because it's like a naturally given system equation on Kähler geometry. Well, this is a highly nonlinear system of PDE, and we know very little to solve it for general compact Calabi-Yau manifold. And so the solvability of this system is in general rather difficult to solve. I conjecture the solvability is equivalent to stability of the gauge bundle, and this was interesting because it was a guideline for us to look into that. And well, we have a interesting balance class in this whole system, namely capital omega, the norm omega naught times omega naught square. This defines an element as a class because d of it is equal to 0. And this is an interesting class because it defines a cohomology class, and it's sitting in H2, 2. And then we have a necessary condition because a normally condition require the second Chern class of the bundle equal to second Chern class of the manifold. So you see this equation 6. The left-hand side says that it is DD bar closed. The right-hand side is the second Chern class of the manifold minus second Chern class of the bundle. In equation 5, we actually know the first Chern class of the bundle is equal to 0, and the first Chern class of the manifold is defined to be 0 because it is Calabi-Yau manifolds. So therefore, we can rewrite this condition to say that it's necessary that the second Chern class of the bundle equals second Chern class of the manifold. In the DD bar cohomology, it's important that it's DD bar cohomology. In Kähler manifold, DD bar cohomology is same as standard cohomology, but not in the case of general complex manifold. So we have to make it clear these are true in the DD bar cohomology. So we want to say that under this condition that I wrote down here, that the Strominger system can be solved. So this is rather interesting question, and I will describe some of the current status of this knowledge. So, well, what do we know? We generalize the Calabi-Yau conditions. For example, if I take the tangent bundle to be the holomorphic vector bundle to be the gauge bundle, and we set omega equal to h, both of them are Kähler and rigid flat, then all the equations are whole because the capital omega, the norm of it is constant, and the small omega is closed, and everything holds trivially. So therefore, we have we can solve the Strominger system if we assume the holomorphic bundle is a tangent bundle with no effort. Well, then it's interesting that we can do a simple thing, and this thing turns out to be not so simple after you look into that. Namely, even a three-dimensional Calabi-Yau manifold, and I get a Calabi-Yau metric. I take a trivial bundle adding to the tangent bundle. So I take R copies of the trivial line bundle, and I take a trivial constant metric on the trivial bundle. Then we still solve the Shing-Tung system in a trivial manner. All equation holds because the curvature of H1 is trivial. It doesn't give you any problem for you. So therefore, for a tangent bundle plus several copies of trivial bundle, we still solve the problem. Now we can make a deformation on the other hand. This was studied by Junli and myself about 20 years ago. We take a small deformation of the holomorphic structure on the trivial bundle plus a tangent bundle. Once you deform that, it becomes a non-trivial question because we can choose a deformation so that it's non-degenerate. And then there's a bundle structure on the non-trivial bundle structure, which is no more a product on this tangent bundle plus trivial bundles. It is trivial product in the sense of topology, but it is not trivial in the holomorphic sense. So we can do it, and we can find out the condition for it to hold, and this can be written down as an algebraic condition on the cohomology class, on the deformation class. So there's a deformation class we can write down for the Shing-Tung system, deforming this bundle. And in fact, these are given by the standard deformation on the tangent bundle and H1 or endomorphism of the tangent bundle plus H1 of O and also C star. So we work this one out in the case of smooth quintic and also on the product of P3 cross P3. So in this way, we construct first non-trivial example of regular irreducible solution to Shing-Tung system with gauge group U4 and U5. So we can solve, therefore, this first time we can solve Shing-Tung system with non-trivial bundles and with gauge group sitting U4 and U5 and is non-singular. So this first time that Shing-Tung system was shown to exist, at least in a reasonable large class of manifolds. Then in around maybe 18 years ago, around 2004, I think, Fu Jiqiang from Fudan, and I construct solution of the Shing-Tung system on a class of non-Kähler Calabi-Yau manifolds, free-folds. These are so-called Calabi-Ekman manifolds. They are T2 bundle, torus bundle over K3 surface. And this was first pointed out by the physicists, but they did not know how to solve this problem at all. They found out these are interesting potential manifolds of interest. But then we immediately found that the Shing-Tung system is very well suited for this class of manifolds. So these are torus bundle over K3 surface. It's a fiber bundle in the sense that the fibers are isomorphic to each other. So in these manifolds, there exists natural metrics. I take a Calabi-Yau metric on K3 surface, conformal deform it by a function, exponential u, where u is any function defined on K3. And I take the connection 1 form on the T2 bundle. So we have a connection 1 form on the T2 bundle, and you take theta wedge theta bar. So as I said, such a metric are interesting, and but in order to make it satisfy the Shing-Tung system takes much more work. So let's look at what the argument that Fu and I use. we reduce the difficult anomaly cancellation equation, which says dt bar omega equal to the second transform of the manifold minus second transform of the bundle, to the following motion pair equation. So exponential u is the same u that we had up here. Exponential u defined on this equation is now appearing here. F is going to be some function obtained by looking at those geometry. A given function to u. Mu is going to be another function satisfy integral mu of omega equals 0. This mu come out from the statement that the second transform minus the second transform of the bundle minus second transform of the manifold is equal to 0. Well, so we need to solve this equation where u is unknown and f is given and mu is given, where mu satisfies this integral equation. Alpha pi is a coupling constant, is a string constant. So this is a motion pair type equation we need to solve. This equation is somewhat similar to the equation appear in the Calabi conjecture, but not the same because we have the Laplacian term appearing here. Quite a few arguments are parallel to what I did in Calabi conjecture, but there's some very key estimate which is not trivial at all, especially the estimate, the volume form of this metric. And this one is rather complicated and interesting, a priori estimate up to third order in order to do this. And this was done in our paper. And this solved the equation. This solved the equation given by Strominger. Well, soon afterwards, so this is rather good because it's the first time we can solve the Strominger system on a non-Kähler, intrinsically non-Kähler complex manifold. Because this manifold we know is non-Kähler. It does not admit any Kähler metric. So we get this solution of heterogeneous string on the T2 bundle over K3. But then one can always replace K3 surface by non-compact manifolds. Say these are ALE space, so non-compact Calabi-Yau manifolds. A simplest one is what people call Ikuchi-Hansen manifolds, which is obtained by C2 cosine by a involution, and we blow it up. It turns out to be cotangent bundle P1. So over this three-dimensional, two-dimensional manifold, we can do the same thing as what I did with Fu. And there, actually, we can write down an explicit metric on the Ikuchi-Hansen metric on the blow-up of the cosine. And this is a exact solution which we write down. And this is a interesting one-one form we can use to choose the toroid and also use as a gauge field. So we can more or less solve this equation, this anomaly equation. So we can write down the anomaly equation, which reduce down to an ODE. So the previous equation we wrote down is on compact K3, which makes things very complicated because we don't even know explicitly the metric on K3 surface. But here we can write down the metric explicitly, and this becomes the equation that we want to solve, this ODE. And this equation, we can solve it, so to speak, explicitly. Namely, you take the coupling constant, alpha pi, the string constant. When it's sufficiently small, we can write down exponential u in terms of a power series expansion. And this, you can prove it to be convergent. What does that really mean? We don't know. So presumably, all this constant would be interesting with some meaning, maybe some meaning on counting something. But anyway, this is solution for this equation. In the case of the manifold becomes a Ikuchi-Hansen manifold. Well, there are many other explicit constructions for non-Kähler Calabi-Yau manifold later. And this was actually I recommended to my former student Phaeton to work on it. So a class of compact non-Kähler Calabi-Yau manifold were constructed by Calabi using vector cross product on R7 coming from Kähler multiplication. And one can construct triple periodic minimum surface in R3 by using Calabi's construction. And this was generalized by Albert Gray later. These manifolds one can construct complex manifold, compact one, using this vector product. And this is a very interesting construction. I recommend you to look at their paper. So their manifold is a total space of certain holomorphic vibration where the fibers are hyperkähler 4 manifolds. For example, T4 or K3 surface. The base manifold is a triply periodic minimal surface in R3. This kind of periodic minimal surface one can find in the literature. So these are beautiful manifolds also. In this case, which is different from what I did with Fu, the fiber is now changing. The complex structure on the fiber are changing from point to point, but change in a reasonable, good, nice manner. So my student Tan Fei, as I mentioned, was using it in his thesis to identify the Calabi-Gray construction by pulling back of the twistor family of the hyperkähler manifold using holomorphic map from a Riemann surface to P1 coming from vanishing theta characteristics. This observation allows him to generalize the Calabi-Gray construction. Fei also showed that there's a natural balance manifold balance metric on any generalized Calabi-Gray manifold. So there's an interesting class of manifold that was constructed by Calabi and generalized by Gray. And these are this is a good class of balance manifolds, which I think deserve to be studied more. And later, Fei went to Columbia as a assistant professor. So he worked in Columbia with several students together. They showed that the full Hull-Strominger system can be solved on a large class of generalized Calabi-Gray manifold. So generalized the work that I did with Fu. And they write down answers solving the conformally balanced metric equation based on the method that I developed with Fu. And by carefully choosing the gauge bundle, they show that the Hull-Strominger system can be reduced to a linear elliptic equation on a Riemann surface, coupled with an algebraic equation, which can be solved explicitly in many cases. So that's very good. You can do that. You can solve it explicitly. So they obtain solution to Hull-Strominger system on generalized Calabi-Gray manifolds whose base could be of any genus greater than or equal to 3. Therefore, they produce solutions on non-Kähler Calabi-Yau free manifolds with unbounded topological types and Hodge numbers. And it's not clear what these manifolds mean in terms of physics, I think. So this would be interesting because there are infinite family of them. Well, one can also study a local version of what they did. And this was actually observed and developed by Chen, Pentaf, and Sharp using a Lander-Ginsburg math model. Now, around the time when Fei was there, and then Fong in Columbia leading his whole group to develop a flow argument, and normally flow argument to solve this equation that Hull-Strominger system wants. They start from a balanced manifold, and then they prove such a flow will preserve the balance condition. This becomes a very beautiful method. And in fact, they were able to understand the argument, simplify the argument that Fu and I did, which takes quite a lot of estimate. Anyway, this were a nice flow and would be interesting to understand them better. So the flow provides a path in the space of balance matrix inside the initial data. Short-term existence is known for the initial matrix with the alpha pi small enough. So in all the arguments, we always assume the alpha pi is small, including in the method that I did with Junli and with Peyton, with Fu. And so this will be very interesting to understand what happens when alpha pi is bigger. But in any case, this was this parabolic approach was used by the group around Fong and Fei. Now, this solved the system that I want, including the balance condition and all that. So when alpha pi equals 0, this is especially interesting condition, I think. But alpha pi small and all that is interesting. But what happens when alpha pi is large is largely an unknown question, which I think deserves to be studied more carefully. Now I'm going into another set that Picard, Collins, Tristan Collins, and I did when we were in Harvard. So they came as a BP and in Harvard. So we studied the Strominger system with fixed balance class. We showed that if these class are the square of a Kähler metric, which admits solution to the system for bundle satisfy the necessary condition. So for a large class of manifold, we solve the conjecture that I made before, that we can solve the Strominger system. But assuming the class, the balance class, come from the square of a Kähler metric. So this is interesting, and let me write down the freedom. So given X, which is a complex manifold dimension 3, equipped with a holomorph vector bundle, volume form, and a Kähler Ritchie flat metric. So this manifold is Kähler, Calabi-Yau. And say we have a bundle satisfy the necessary condition, namely the second trend class of the bundle equals second trend class of manifold. And suppose E has degree 0 and stable with respect to this balance class. So degree 0 is necessary because we need to make sure the Strominger system holds. Then we prove that if the balance class is large enough, namely the norm omega square equal the big number m0 times the fixed omega square. If m0 is large enough, we can solve the Strominger system. So this is good, assuming that we have a square of a Kähler metric, and then we can solve the system on any Kähler manifold, but assuming the class is large. So the cone of balance classes actually was quite interesting. On the other hand, in this theorem, we assume that it is coming from Kähler class. So rather restrictive turns out, because it was found by Fu and his student that the cone of balance class is much bigger than the square of a Kähler metric. So not every balance class will come out from square of a Kähler metric. So the balance cone becomes an interesting invariant for a Kähler manifold. Even though it is a Kähler manifold, the balance class could be larger. So therefore, we need to generalize this theorem that I did with Tristan Collins and Picard to more general situation. So this is still an interesting question to do. Well, now we will discuss non-Kähler geometry in general, in topology and algebraic geometry. A fundamental open question is to understand the possible topological types of Kähler Calabi-Yau manifolds. And now here we know there are a huge number of distinct Hodge diamonds, which make physicists unhappy because there are too many of them. And this is a big landscape which they don't like to see. But we would like to say how they look like. And this was motivated by a proposal mentioned by Myers Reed. We actually did not really have the guts to call it a conjecture. They call it fantasy, which is fine. We call it fantasy. And this was developed by Clemens and Freeman. And so, so we like to talk about that. There's another proposal was made by Philip Candelas and Green and also Tristan Hobbs, who was also my postdoc before. So there's a geometric transition that we like to discuss now. As I said, proposed by Clemens and Freeman, and then later by Myers Reed. So you go from a Kähler manifold to non-Kähler Calabi-Yau manifold. So what the fantasy is that every Calabi-Yau manifold can be deformed to each other, but the deformation go through non-Kähler Calabi-Yau geometry. This is rather bold, and if it's true, this would solve many questions that physicists doesn't like, because they do not like they are all distinct. There may be huge number of them, but if they are all connect them together by some standard canonical procedure, that will make you feel that they are just one piece in any case. So this is interesting in any case, because this may tell you how the topology of Kähler free manifold moves around when you go through some bleachers through this transition. So I would hope that the Strominger system will play a role for this transition. That's one of the reasons I'm interested in this Reed's fantasy. So what is that? So given a Calabi-Yau manifold, we have a lot of P1 rational curves. The rational curves have normal bundle given by O-1 plus O-1. So there is a rank 2 bundle. The normal bundle is equal to O-1 plus O-1. So this P1 can be brought down to be a rational double point. So these are the rational curves that play a role in Miller symmetry a great deal. So what you do is to contract this curves into a point. This becomes a singular Calabi-Yau manifold because of once you contract it down, it becomes a rational double point. So given quite a few of these curves, now we end up with quite a few rational double points. And if we assume a condition put down by Freeman, namely summation lambda I Ci, Ci is the rational curve, the class is equal to 0 for non-trivial lambda I. It turns out we can deform these singularities into non-singular manifolds. So why, therefore, which is the Calabi-Yau, we collapse some rational curve to singular points and then smooth it out. It becomes non-singular complex manifold, which is still Calabi-Yau. Namely, the holomorphic free form, which was given to you on Y, still survives. The reason it still survives because the free form correspondent divisors. Here we just perturb curves, so it doesn't destroy its existence. So after this procedure, XT is still a Calabi-Yau in the sense that it admits holomorphic free form. And this is interesting because the local smoothing of the rational double point can be written down in this way: summation square equal to T. When T is not 0, it becomes a non-singular thing. So this smoothing condition set by Freeman was infinitesimal deformation was proved by Freeman that the first order deformation is fine. And the general case was worked out more showing that the Collier-Spencer obstruction can be done, was done by several authors. And so now we know that we can always make it to be a non-singular manifold. So what we have achieved is that, according to Myers Reed, given a Calabi-Yau manifold, we can obtain a X where we destroy most rational curves in that way. So the construction decreases x1, 1 because we collapse the rational curves, and x2, 1 go increase. So eventually, you will see that the manifold becomes Cornet sum of S3 cos S3. So topological change is such that the number of nodes, the second Bethe number decreases by k, and the third Bethe number increases in that way. So, so as a result, we can eventually destroy all the rational curves, and yet destroy not all rational curves, destroy all the Bethe number, second Bethe number, and yet we increase the third Bethe number, and eventually you will become a Cornet sum of S3 cos S3 in many copies. So as a result, what do we get? We go from a manifold and any Calabi-Yau manifold to some interesting models which we know the topology well. Namely, they are S3 cos S3 Cornet sum itself many times. And this manifold still admit a holomorphic free form, but it does not admit any Kähler metric because the second Bethe number is equal to 0. So these called conifold transitions that move a Kähler Calabi-Yau to a non-Kähler Calabi-Yau, and it's still trivial canonical bundle. So what we fantasy says that all the Calabi-Yau manifold can be connected in such a form. So this would be interesting to know whether this is true or not. And turns out Candelas and Green and Tristan Hobbs has demonstrated that this fantasy actually works for complete intersection Calabi-Yaus. But one still need to make more evidence to support such a conjecture. But anyway, to make it well, even in some interesting cases, I think would be very interesting. So I was hoping to make the transition to have an interesting geometry linked with them. So in the case of Calabi-Yau, we have the Calabi-Yau matrix, Ricci flat matrix, which is canonical. And I like to use the Hull-Strominger system to make the conifold transition to have geometry associated with it. So during the transition, we like to see how we build up this Hull-Strominger system. Well, an important statement was done by Candelas and De La Osa, where they construct Ricci flat Kähler matrix on the local conifold transition. So when you go from a local singular point, summation Ci square equals 0, there's a bundle, O minus 1 plus O minus bundle over here, and you move to the non-singular one. So we want to see some interesting Ricci flat metric can be created out of this. So let's say we are trying to understand the bundle that we have interesting for heterogeneous string to be the holomorphic tangent bundle itself. So therefore, there's no problem about topological condition because the second trend class are the same. So I want to see how this Hull-Strominger system can be resolved by using this matrix created by Candelas de la Osa. So what did they do? They construct on this manifold summation Ci square equals 0. They construct this canonical Ricci flat cone metric. So this is a metric on the cone. On the rational double point, they just write down this metric, summation Ci square to the power 2 of 3. Well, we can write down a family of metric on the resolved conifold. When you resolve the rational double point, we can parameterize a family of metric over there, which given by constant A, which measures the volume of the P1s appear in the resolution. And this can be done by symmetry, by using ordinary differential equation method. So we use the Kähler-Osa metric, and then we construct a family of metrics on there. And this metric will be convergent to the one with A equals 0. Now, similarly, we can also construct on the smooth conifold. We can construct ODE method as some family of canonical metric over there. So the first class of manifold is obtained by resolution. The second class is constructed by deformation. So this two family metric has a property when A equals 0, which means that you scale the exceptional curve to 0, to trivial. Or in the case of deformation, let the deformation parameter go to 0, they obtain to be the same metric. So this gives rise to an interesting class of asymptotic canonical Calabi-Yau metrics. And this was interesting that we want to prove that the Y manifold, the non-Kähler complex manifold obtained by the Clemens construction can admit a balanced metric. This was proved by Fu and Junli and myself about 10 years ago. Given a compact Kähler Calabi-Yau manifold, we go for the conifold transition, and we found this new class of manifold, and then we proved that this new class of manifold actually admits a balanced manifold matrix omega t. The omega t square is closed, and these are good in both class X and Y. And so these are convergent to the Kähler-Osa matrix in the local conifold transition. So this was actually a non-trivial argument. Many people try to claim it by waving their hands, but it's not clear at all. So we actually, with enough effort, we proved the existence. So this now we know the whole procedure in the conifold transition, we actually have interesting metrics, namely balance metric. Well, with the balance metric, we like to see what we can do for this balance metric. My former student Chong in 2012 solved the Hermitian connection with respect to this balance metric through conifold transition, provided the bundle is holomorphic trivial near the residual curve, which is contract. Well, it's not clear this condition is compatible with the anomaly cancellation equation, which is non-trivial to solve. So we still would like to deal with the anomaly cancellation equation. And so in this case, we like to assume the bundle, the natural bundle, to be holomorphic tangent bundle. And then a few years ago, Tristan Collins and Picard and myself work on this, and we can understand it and solve it. So in this conifold transition, we have this balance metric constructed by Fu, Junli, and myself. We can prove there exists Hermitian metrics on the tangent bundle Y and the tangent bundle X. So both of them are tangent bundles, and we solve the equation that we want. So these are interesting, and I think this is a interesting questions that shows that we have a nice set of equations that we like to deal with. I don't have that much time to go through the argument, but here is the sketch, and we produce singular Hermitian-Yang-Mills metric on a singular space, and then we construct this smooth family balance metric come from Fu and Li and myself. And then on the stable bundle, we can use the argument that I did with Junli to construct those Hermitian-Mills construction. And then we do a singular perturbation to achieve what we do. So this was written in our paper. I hope you can take a look. Well, what is remaining to be done is very interesting and is still not understood well. Namely, is to understand the moduli space of solution to the Schrödinger system. So we are able to construct existence in many important cases, but the actual understanding on the moduli space are important. And this was done by several group of people in the math literature. I hope you can take a look at that. But this is rather interesting, what the moduli space is supposed to be, because the Schrödinger system, how to make it understand its ellipticity and all that turns out to be non-trivial. And also how to make sure the uniqueness holds and all that are also non-trivial. So one still need to explore what's going on with that. So there are large number of interesting questions remain to be seen. And what is the actually the role that they play in media symmetry is also left to be seen. And I hope many of you can continue this class of research, because this is really the first important class on non-Kähler complex manifold that have interesting structure. And this is motivated by heterogeneous string theory, which means that it has some substance, I hope. Okay, thank you very much.